So there's an 8-foot wall, and I assume the wall is going to be standing upright, so there's going to be the ground and the wall standing up. And then find a beam that will reach from the side of the, it's gotta draw a building. It doesn't say how tall the building is, so just make it really tall. And then the beam has to go from the ground outside the wall. So from out here somewhere, it has to hit the ground. I guess this person is trying to break into this building. They need to get over this wall, and they've got a plank of wood, and they need to know how long does this wood have to be so that they can get over the wall and then get to that building. So I need to extend the ground here. So there's the setup. And now we have some variables like find the length of this plank right here, or this beam. And then we've got that there's a 27 in there, that the 8-foot wall is 27 feet away. This part is not known, so I'll just use X. And then I can see that Pythagorean theorem is most likely going to be used, so we need something on this. We'll call it H. Okay, so we could use the Pythagorean theorem. This whole big outside triangle has x plus 27 as one leg and h, and then there's the hypotenuse. So we'd have L squared equals h squared plus x plus 27 squared. And then we really need to get L to be a function of x only, so we need some other information about h. And I can't really use the Pythagorean theorem again because, well, this is my only other right triangle, and that doesn't involve h. I need something that has h in it. Well, what I'm going to use is similar triangles. So there's this triangle that's a little right triangle, and it has this as its angle across from the 8. There's also this big triangle. It's got this same angle down here in the corner. It's got x plus 27 as this, and h as this side. So then I can do a comparison like h over 8 is going to be the same ratio as x plus 27 over x. And then all we have to do is multiply by 8, and we have what h is equal to. All right, now substitute that into our L squared function. So it's going to be an 8 and x plus 27 over x, that's squared, and then x plus 27 squared. And then notice that both of these have x plus 27 squared in them, so I could factor that out. So I'd have x plus 27 squared that gets factored out, and what would be left is an 8 over x squared, so that's 64 over x squared, plus I factored this out, so it leaves behind a 1. And then the next thing to do is take a look at the graph and see we're being asked for a minimum. So see if this thing even has a minimum. So there's the function. And then if you change the window to 0 to 25, and perhaps this doesn't need to be 20,000, let me try 2,000. Then take a look at the graph. And 2,000 is not enough. So rather than doing guessing and checking, I'm just going to go to trace and see where are these numbers for the y value. They're in the 2200s, so this perhaps I should go to, let's go to 4,000. Sure enough, it does have a minimum, so we should proceed. Now, With this, we could take the square root, and then we would have the square root of all this stuff, and we need to take the derivative and set it equal to 0, which would be quite a mess. But the thing is, if you're trying to find the minimum of L, that's really finding the minimum of L squared. So you can do either one. So for example, if it turns out that the minimum for L is equal to 10, then the minimum for L squared is equal to 100. And likewise, if you found out that the minimum for L squared is 100, then the minimum for L is going to be a 10. It's not like you can have, well, the minimum for L is 9, but the minimum for L squared is 100. No, it would then be 81. So my point is that you really don't have to worry about the square. You can just find out, pretend this is just L. So we're going to then take the derivative. So I'm just going to say we're finding out what's the minimum of L, and now take the derivative. So we're going to have to use the product rule. So derivative of the first one would look like this, and then the second one left alone, and then plus the x plus 27 squared left alone, and then take the derivative of this. Well, this is essentially x to the negative 2. So if we take the derivative, that would be negative 2x to the negative 3, or in other words, negative 2 over x cubed. So we'd have negative 2 over x cubed, and then that's times a 64. And then derivative of the 1 is 0. Okay, so one thing to do is find out where this is undefined. That would be x equals 0. But if x equals 0, then this board, which would be supposed to be going this way, if x is equal to 0, that means this point down here has to go like this, and it would be very difficult to walk up that board and get to the building. So x equals 0 is not realistic. We could also, let's see, do some algebra. That one has x plus 27, that one has x plus 27, so set it equal to 0 and factor out an x plus 27. And what's left behind here is a 2 times this thing. So 2 times 64 over x squared plus 1. Factor out an x plus 27 out of that one, it leaves behind an x plus 27 as well as this. So then it's plus an x plus 27 multiplied with, this is a negative 128 over x cubed. So now that it's factored, set the factors equal to 0. But if you set this one equal to 0, it says x equals negative 27, which would then mean that the board is starting over here and going that direction. So that's not going to be going up the building. So that one's not going to give us a solution. And so next it's going to be all of this set equal to 0. So we'd have 0 equals, that's going to be a 28 over x, 128 over x squared plus 2. And then this I should distribute, so negative 128 times an x, but over x cubed. So that reduces to be a negative 128 over x squared. That's a strange coincidence. And then a 128 negative times a 27. So negative 128 times a 27, negative 3456. I just thought that's strange also. Look at this. So this thing shows up both positive and negative, and then the next number it shows up, 3456. Math is funny. Over x cubed. So these guys cancel each other out. I can take this one that's negative, put it on that side. So 3456 over x cubed Oh wow, would you look at this? Now you've got 2, 3, 4, 5, 6. All right, so divide by 2 and multiply by x cubed. So x cubed is equal to 3, 4, 5, 6 divided by 2. 3, 4, 5, 6 divided by 2. 1728. All right, now just take the cube root. The cube root of 1728. Wow, turns out to just be a 12. So x is equal to 12, but that's not the length of the board, that is this right here. So now we need somewhere to find out what should L be. So I think we need to go back to this one and substitute for x. So we're going to have x is a 12, so this is going to be 12 plus 27, a 39, times an 8, divided by the x, which is 12, and then that's squared. And then this is the 12 plus the 29 is 39 squared, so plus another 39 squared. And so finally take the square root of that. So the board or beam should be 46.872 feet long.